Alright, this is section 4.4, real zeros of polynomial functions. So the first thing we want to know is the factor theorem, which says that x minus k is a factor of f of x if and only if f of k equals 0. Or we can think of that as x minus k is a factor of f of x if and only if k is a 0. And that just means f of k equals 0 means k is a 0. So, for example, if x minus 2 is a factor, then 2 is a 0. Or if 2 is a 0, then x minus 2 is a factor. That gets tricky when you have negative zeros, like negative 1. Right? So if negative 1 is a 0, x minus negative 1 is a factor. X minus negative 1 is just x plus 1. Which the other way, if we think x plus 1 is a factor, then x minus negative 1, x plus 1 is x minus negative 1, so negative 1 is a 0. Alright, so let's take a look at what should we be able to do with that. Number 1 says list all the factors of f of x. So to find the factors of f of x, we look for the zeros, and the zeros on a graph show up at the x-intercepts. So there's x equals negative 1, x equals 1, and x equals 2. So we have the zeros, negative 1, 1, and 2. Right? Negative 1, 1, and 2. There they are. And then to build the factors, we just take x minus each of those. So x minus negative 1, which is x plus 1, x minus 1, and x minus 2. Those are the factors that are included there. There may be others, but those for sure are there. Okay. Let's look at something else, and that is the complete factored form. The second part here. And that says that if you have some polynomial, then the complete factored form is of the form f of x equals a sub n x minus c1 times x minus c2 times x minus cn, where each of those c sub whatever it is, c sub 1, c sub 2, and all the way up to c sub n are zeros, right? And what that means is, sometimes we have an f of x that factors into something like maybe 2x plus 1 times x plus 2. Complete factored form cannot be cannot start with a 2. It has to be written like this: x minus c1, x minus c2. Notice there's no 2x minus, right? So we can't write a 2x in complete factored form. But that's easy to fix. We just factor out the 2 from that factor. So if I factor out the 2 from 2x plus 1, remember I'm dividing through by 2, so it'll be 2 times. If I divide each of these by 2, I get x plus 1/2. So it'll look like this. F of x equals 2 times x plus 1/2 times x minus 2. Notice again we can go backwards and consider what would be the zeros. These are the factors. What would be the zeros? Well, this is x minus 2, so 2 is a 0. And this is x minus negative half, so negative half is a 0. Okay? Alright, let's continue with the next example. It says the graph of a polynomial function f of x with a leading coefficient plus or minus 1 and integer zeros is shown. In the figure, write its complete factored form. All right, so the first thing is, what do these mean, a leading coefficient of plus or minus 1? Well, they're telling us that the leading coefficient is either 1 or negative 1. We have to figure out which one it is, which one of those two it is. And the integer zeros means that the zeros, or the x-intercepts, are at the integers, right? That means it looks like it's close to negative 3 here. That means it is negative 3 because they're integer zeros. Alright, so we're going to start the same way as we did up here by writing the zeros. So the zeros are negative 3, negative 1, and 1. There they are. And then we're going to build the factors. So it's x minus each of those. That's x minus negative 3, which is x plus 3, x minus negative 1, which is x plus 1, and x minus 1. Alright, so my factors are x plus 3, x plus 1, and x minus 1. Okay, now I gotta write the complete factored form. So I have the factors. I just need the leading coefficient, but I've been told it's either a 1 or negative 1. How do I know? Well, it brings us back to, leading coefficient of this polynomial. So if I look at the line that connects this end to that end, that line would have a positive slope, and so the leading coefficient of this polynomial is also positive. So it'll be the positive 1. Okay? So our complete factored form is 1 times, that's the leading coefficient is 1 times x plus 3 times x plus 1 times x minus 1. And notice I don't write the 1 because we don't write 1s. If it's only a 1 like 1x, we don't write 1x, we write x. Same thing here. So base of n is 1, we just don't write it. If it was a negative 1, by the way, we just write the negative in front. Okay, let's try number 3. The graph of a polynomial function f of x with integer zeros is shown in the figure. Write its complete factored form. So I'm going to start the same way. So the zeros are negative 3, negative 2, negative 1, and 1. So the factors are x minus each of those, right? So x minus negative 3, which is x plus 3, x minus negative 2, that's x plus 2, x minus negative 1, that's x plus 1, and x minus 1. Those are my factors. So I just need to write something like this, except I don't have an idea what a is at all. It says the leading coefficient is not plus or minus 1. So I need to just find it from scratch. How do I find it? So this is what I have so far. Let's write down what I have. So I have f of x equals, I'm missing the a, so I'm just going to write a, times x plus 3 times x plus 2 times x plus 1 times x minus 1. Okay, and this is something we've done before. We did it with parabolas. But to find a, we look for a point that we can see on the graph that is not one of the zeros. Okay, we just don't want one of the x-intercepts. But if you look close, right there is the point 0, 2. It's on the graph. It can be any point. I just can't tell where the other points are. But 0, 2 is on the graph, right? The point 0, 2, which means x equals 0 and f of x equals 2. Okay? And what I'm going to do is I'm just going to replace, oops, this is x, not 0. X is 0 and f of x is 2. So I'm going to replace x with 0 and f of x with 2 in what I have right now. So f of x will be 2 and x, each of these x's will be 0. Okay, so f of x is 2 equals a times 0 plus 3 times 0 plus 2 times 0 plus 1 times 0 minus 1. Right, each of those x's is 0. Alright, so I have 2 equals a times 0 plus 3 is 3, 0 plus 2 is 2, 0 plus 1 is 1, and 0 minus 1 is negative 1. So that's 2 equals, and 3 times 2 times 1 times negative 1 is negative 6. So I'll divide by negative 6. Remember, I'm solving for a. That's why I'm dividing by negative 6. And so I get a equals negative 1/3. Okay, so now I know what to put in place of a, and I'm done. I'll have f of x equals negative 1/3 times x plus 3 times x plus 2. I'm just copying these over. Times x plus 1 times x minus 1. Okay, there's my complete factored form. Alright, let's try the next page and we'll start it and we'll see how far we can go. Alright, so we're going to look at something called multiplicity. Multiplicity is something as follows. So if f of x equals x plus 2 squared, notice the exponent, then the factor x plus 2 occurs twice, right? Because x plus 2 squared is x plus 2 times x plus 2. Each of those gives us a 0, negative 2. They're the same. So the 0 is negative 2. Because it occurs twice, it's called a 0 of multiplicity 2. So the multiplicity just says how many times it occurs, that same 0. Okay? Now, if we're looking at a factored form of a polynomial, we can see the exponent and tell the multiplicity. However, if we're looking at a graph, how do we know what the multiplicity is? Well, we look at how it crosses the x-axis, or how the x-intercept occurs. Remember, zeros, we can see them as x-intercepts. So here's a 0. Its multiplicity is 1. How do I know? Because the curve, it just crosses straight through. It doesn't bend. And that's what you're looking for, bending. Okay? Multiplicity 2 actually bends like this. It just bounces off the x-axis. If it's coming from the top, it bounces back up. If it's coming from the bottom, it bounces back down. Multiplicity 3 bends like this. It crosses, but it bends. And multiplicity 4, again, bounces off, whether it's coming from the top or from the bottom. Okay? So a multiplicity 1, a 0 multiplicity 1 on the graph will look kind of like this. The graph will just cross without bending. Multiplicity 3 will cross, but it'll bend. Multiplicity 2 will bounce off. Multiplicity 4 will bounce off. So it turns out that odd multiplicities behave very similar. They cross, but just multiplicity 1 doesn't bend 3 bends, 5 bends, 7 bends, and so on. Multiplicity 2, 4, 6, 8, any even multiplicity bounces off. What's the difference between multiplicity 2 and multiplicity 4? Just multiplicity 4 flattens out a little bit more when it touches the x-axis than multiplicity 2. Okay? All right. So we're going to continue on number 4. Let me see. No, let's finish number 4. So write a polynomial f of x in complete factor form that satisfies the conditions. Let the leading coefficient be 1, so our a is 1, degree is 4, zeros are 5 and 7, both with multiplicity 2. Okay, so that means my factors, because they both have multiplicity 2, are going to be x minus 5, I'm sorry, but with a square, right? So that's x minus 5 squared, and this will be x minus 7 squared. So if I write complete factored form, it's going to be f of x equals the leading coefficient, which they told me is 1, times x minus 5 squared times x minus 7 squared. And notice that's degree 4. Okay. I think I'm going to leave it there and continue on the next video. So we'll pick up on number 5 on the next video.